We opened with the point that in a very large fraction of chemical reactions, it's important to exercise exquisite control over those reactions. And the most dramatic example of that are the reactions that take place in the human body. They are in delicate equilibrium, and they need to be maintained, and they need to be controlled to a very high tolerance. It's also interesting to note that the industrial processes that are used to produce vast quantities of chemicals globally are also equilibrium reactions. So let's come back to our Haber process. And that Haber process, again, involved the reaction of gas phase nitrogen. And that gas phase nitrogen has a triple bond. It's one of the strongest bonds in nature. And when we react that with hydrogen, gas phase hydrogen, to form the molecule NH3, or ammonia, which also comes off in the gas phase, and we need to balance that equation. The fact that this reaction takes place at all is remarkable because of the strength of that N2 bond. And let's just keep track of the fact that in order to drive this reaction in a way that is effective on large scale, because we have to produce fertilizers that are distributed on crops across the world, we typically run this at temperatures about 720 Kelvin, and we operate at pressures around 20 atmospheres, and we do this over an iron catalyst. And this was the combination that Fritz Haber used in the late 19th century to recognize the way in which the production of ammonia could be brought to large scale. Now, it's also true that this helped humanity dramatically because it increased the productivity of crops worldwide. Unfortunately, the nitrate that can be extracted from the ammonia was used as an explosive, and it was the primary explosive used in the First World War. So there were good aspects and not so good aspects of the development of the Haber process. And it's interesting to look at how this actually occurs, because we feed N2 and H2 into a chamber and we use a compressor. The compressor is used to create the 20 atmosphere pressure inside, and then the gas comes in and it circulates through the system, and it's raised to 700 Kelvin, a quite high temperature, across this iron catalyst, and out of that mix comes ammonia and unreacted nitrogen and hydrogen. And remember, the reason for that is that when we look at the Gibbs free energy surface, that Gibbs free energy surface initially drives the reaction in a spontaneous way that creates a mixture of ammonia, hydrogen, and nitrogen. So Gibbs free energy at the particular temperature and pressure establishes this mixture of ammonia and unreacted nitrogen and hydrogen. So a refrigeration unit is used with a condenser to convert that gas phase ammonia to a liquid, and that comes out as the product. In this case, it's NH3 in the liquid phase, and then the unused nitrogen and hydrogen is brought back in and recycled through the system. So nitrogen and hydrogen is increased by the addition of more nitrogen and hydrogen. The compression occurs again, and the cycle goes continuously. And the question is, when you're designing a system like this, how does this chemical equilibrium process play into the design of the system? And to analyze that, we have to look at how changes in pressure, temperature, concentrations play into the shift in that chemical equilibrium.